Hello, welcome back. For this next section, we're going to look at sound waves. So we're going to start with how do we hear things. So the way we hear things, if you have a speaker, the speaker is thumping. It's compressing the air, and these compression packets travel through the air. They go into our ear, and our brain is able to transmit or transfer that information. There's a video here that talks about it in a little detail. I'd like you to please go into the notes, click on the video, and watch it to get a little more information on that. Properties of sound waves. So sound waves is one of the few waves that is a longitudinal wave. And if you recall, longitudinal waves travel in the same direction of motion. So that would be as if I pulled the spring towards me and then released it. So my hand is not going back and forth. My hand would be going, if my lab partner and I were holding a spring, I'd be pushing the spring towards my partner and then pulling it away from my partner. So it's creating waves in the same direction of movement. Sound travels fastest through solids. It travels slower through liquids, and it travels slowest through gases. And the reason for this is because in solid objects, the atoms are so close together that sound is a vibration of the material. So when sound hits it, the atoms are so compact that one atom hits another, hits another, hits another. And so it's very efficient and easy for sound to travel through solids. Or if you think about gases, where the atoms have more space between them, there's more energy loss and more time in between collisions, and that's going to decrease the effectiveness of sound traveling through those materials. Please note this is opposite of EM waves. So with EM waves, light travels fastest through gases, slower through liquids, and slowest through solids. So it's the reverse between sound and EM waves like light. So what happens if we were to remove the medium? So if we place a bell in a jar and remove all the air inside the jar, what do you think would happen to the sound? I'd like you to take a second, choose one. Will the sound get quieter? Will the sound get louder? Will the sound disappear? Or will the sound change notes? So think about that for a second. What will happen to the sound of a bell if we remove the air around the bell? So here's a video kind of showing it. We have a bell inside this jar, and it's connected to a pump. So the pump is going to remove the air from inside. It's going to create a vacuum. And we could actually do this in the classroom. However, we're not in the classroom right now. So here's a video. You can take a look and see what happens. So sound requires a medium to travel, which is why in the previous video, you should have heard that when they sucked the air out, you can no longer hear the bell ringing. And this was known for a while. In the movie Alien, the tagline for the movie is "In space, no one can hear you scream." It's kind of fuzzy down there at the bottom. That was a tagline for the movie, and it's true. And some Hollywood movies get it right, and some do not. Here's a couple of videos. The first one is from Star Wars, and all the explosions, you can hear them. And that is not the way things would actually happen. Laser beams being fired, you hear pew, pew. Could not hear laser beams. Why would you be able to hear light? It doesn't really make much sense. Hollywood definitely gets it wrong there. And this one is a video from Star Trek. And in this one, they do get the science right. They're jumping from high orbit onto this drilling platform. And as they're falling, if you take a look and a listen, you will notice that there is no sound other than their breathing. And then as they enter the atmosphere, sound gets louder and louder as you can actually hear them falling. So take a look at both those videos so you can kind of see the difference of Hollywood getting it right as they did in Star Trek and wrong in Star Wars. So loudness. Loudness or volume is measured in decibels. I'm not sure why the D is little and the B is capitalized, but that's the way it's measured. And it is the amplitude of the sound wave. So remember, sound waves are compression waves. They are longitudinal, so that thickness of the compression would correspond to the loudness of the wave. And it is a logarithmic scale, so it's not a linear scale. Um, but you can kind of see the differences between different decibels from faint all the way up to loud and traumatic. Pitch. So pitch is the frequency of a sound wave. Pitch and frequency mean the same thing. And so the units are hertz, of course. And high pitched means high frequency. So examples would be treble, squeaky sounds, Mariah Carey. It's kind of way up here, really, really squeaky and really high. And low pitch is low frequency. These are your bass, your subwoofers, deep sounds. This is Morgan Freeman, or if you talked way down here, this would be low pitched. And so there's two videos where you can click and watch, hear some low pitch sounds. And the human hearing range. So if these are your low pitched, your lower end, these are high pitch. You can hear that dogs, for example, can hear much higher pitches than we can. It's not that the sounds aren't there or not that they're not loud. It's just that we don't have the capability to detect them. And that is it for this section. Once again, hopefully you enjoyed it. Hopefully you learned something, and have a great day, Padres.